Hello, this is the solutions for our Unit 3 practice exam, and there's a copy of it on Canvas. But I would like to work out the solutions for you step by step as we go through. And here's a terrible sketch of the function f of x equals minus 2x to the fourth plus 6x squared plus 1. And sketched it using the calculator, of course, and then you got some points using some calculus. So taking the first derivative, use the power rule, so it gives you minus 2 times 4, or minus 8x cubed, plus 2 times 6, or 12x. And then, in this unit on extrema, we know that the places where extrema occur have horizontal tangent lines, therefore their derivative has a value of 0. And so we force it to be 0, and then we solve for that 0. So I've gotten to the stage where I factored, and I have two factors that when multiplied together give me 0 for a product. So one or both of them has to be 0 in order for this to happen. So I allow for the possibility that both of them could be. So that means x equals 0, or x, well, let's take it a step at a time. 2x squared equals 3, x squared equals 3 halves, x is plus or minus the root of 3 halves. And in a decimal, that turned out to be 1.22 plus or minus. So this is a critical value. Or actually two of them, a plus and a negative. And this is a place, or places, where extrema could occur. No guarantee, but it's worth checking out. So we plug this into the original function. And I think I'm going to erase what I was starting to do next and say that we plug this into f of x, and we plug in, whoops, sorry, yeah, that'll work, 1.22, and we get it to be negative 2 times 1.22 to the fourth plus 6 times 1.22 plus 1. And it really doesn't matter whether I use the plus or the minus, because when you raise it to an even power, like I should have done here, it's going to make it a positive anyhow. And when I did that, I got 5.5. So that means my coordinate pairs that could be the extrema are 1.22 for x, the critical value, and 5.55, the value that could be the max. And I also have negative 1.22 and 5.5. So I'm going to call these, according to my graph, the absolute max. And there could be two of them, twins. And this guy looks like he's going to be the relative min right there. And let's see, what else we need to find? Label the points appropriately on the graph: relative absolute max, relative absolute min, points of inflection, concavity, and regions of increasing or decreasing. Well, if you look at the Canvas sheet, you can see all that's done for you. Oh, no, not increasing, decreasing. We can do that. But we could certainly, and we could do that right now. We could say that it's increasing up until the max, so increasing here, and then it's going to decrease down to this relative min, increase again, and when it gets to the other max, turn down and be decreasing. And I probably should get another color for concavity. And to determine the exact place where concavity switches, we actually need to use the second derivative. So I'm going to take my first derivative and take the derivative of that. So I'm starting all over again with a new problem. So I'm going to have minus 24 x squared plus 12. And to find points of inflection, I need to find the place where concavity changes. It goes from a positive to a negative. Hence, it has to be 0 there. So we'll force it to be 0. And then we'll do like we did on this problem where we do what we can to solve. So factor out a negative 12, leaving behind 2x squared minus 1, forcing it to be 0. And equating this number to 0 would be meaningless, but we could say 2x squared minus 1 could be a 0 factor, producing a 0 product. Continuing, equals 1, equals 1/2, equals x equals plus or minus the square root of 1/2, which is approximately 0.707. I'm going to take you back to the other screen. So on this graph, we're going to say that these points, 0.707 and negative 0.707 with their y values of 3.5, are the places where concavity changes sign. So we're going to have concave down here, and on this interval, the small one here, we're going to have concave up. And then we're going to have concave down again. So multiple things can happen. You can have something concave down with an increasing part and a decreasing part. Something that's concave up with a decreasing part and an increasing part. So then we can answer the questions in part B. Where on the interval is the graph increasing and concave down? So increasing and concave down, we could say, well, it's concave down all the way from here to here, but it's not increasing after it reaches the max. So it can only be increasing and concave down from where our interval starts at -2 to where we encounter our max of -1.22. So we probably need a place to write that, huh? So let's erase some here and write the answer to 1B, increasing and concave down from -2 to -1.22, or you can pick that same thing up from 0.707 to positive 1.22, because it's increasing on this little stretch as a change concavity there. So it's increasing from here up, but we have to couple that with concave down. So this is the only little wing possible. So increasing from here to here, but concave down starting right there. So we can only have this little bitty stretch here from 0.707 up to the max, because after the max we have decreasing. So 1.22. Now, these are x values. These are intervals. And it looks like a point, but it's not. So you have to be careful with math. So many things are just used and reused, and you have to be aware of the situation. Notice also that these are soft-sided intervals. That means these endpoints are not included. And we hardly ever include the endpoint because we don't know what's happening otherwise about it. Some people would. I wouldn't mark it wrong if you wrote that hard-sided. I really wouldn't. It's sort of being picky to say it has to be soft-sided. This one, however, has to be soft-sided because at the max, it's neither increasing nor decreasing. So here we could say this one is soft-sided definitely because that's the point of inflection and there's no concavity there. It's got a 0 value. So it has to be soft-sided. This one has to be soft-sided because it's a max again. This one, it's up to how picky to be or don't want to be. And we get the picture otherwise. So we're getting plus or minus the root of 1/2, which is approximately, with this marker, so we're getting the plus or minus the root of 1/2, which is approximately plus or minus 0.707. So I'm going to switch it back to the graph, and we're going to look at where those points are located. I have my positive 0.707 here, negative 0.707 there. The accompanying y value is 3.5, which I got from my calculator by doing the value activity. So there's where my concavity changes. So I'm going to label, let's see, what color can we use? How about red? That my function is concave up here, and I'll use green for concave down here on both sides. So, beginning of the interval is increasing up to the max, and then decreasing down, actually to this place. Oh, we didn't label this, did we? What do you think that might be? I bet if we plugged in x equals 0, we would find out that we have a local min for this interval. Let's even call it absolute. At x equals 0, and the y value would be 1. Put back in the original equation. So we have increasing function up to our max, decreasing down to the min, increasing up to the other max, and then decreasing down. But it overlays with the concavity. It overlaps. So we have concave down that has a wing descending, decreasing, and a wing that's increasing. Same way over here. An increasing wing, a decreasing wing. Over here, or in this area of concave up, we have part that's decreasing, part that's increasing. So to answer the questions that are asked in part B, it says, where are the intervals where it is increasing and concave down? So increasing and concave down, we have to see where they both happen at the same time. So let's see, what color haven't we used? Maybe blue. So increasing, 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 but concave down. So once we get up to the max, we can't or won't be increasing anymore. So we have to say for part B, that is increasing and concave down from the end of the interval, and you can make it hard-sided if you want to include that, up to negative 1.22. And then there's another region we can say, or it's increasing and concave down from 0.707 to 1.22. This little stretch right there. Increasing, but on a concave down wing. Now, it made it hard-sided to emphasize, because when they're both soft-sided like these, and they have to be, it looks like a point. But these are all x values. They tell us where to look. There was an interval from -2 to -1.22, is the behavior we're looking for. Also, from 0.707 to 1.22, x values. So it's a stretch on the graph where that happens, from this x value to that x value. And again, they're soft-sided because if you put negative 1.22 in, it's neither increasing nor decreasing there. It's a maximum. So can't include that point. And 0.707 is an inflection point where concavity is changing. So we can't include that either. And likewise with this max. So we're looking at those stretches, negative 2, the end of the interval, up to 1.22, that set of x values, and 0.707 to 1.22, that set of x values. All right. Oh wait, there's a C too, isn't there? On yes. Where on the interval is, whoops, the board moved, is the graph decreasing and concave up? Decreasing and concave up. Well, just have a little red patch there where it's concave up. So we need the part that's decreasing. So looks like that's going to be just this little section here. So part C, we're looking for decreasing, whoops, and concave up. And we said it's just this little stretch here where it's on the concave up section, but the decreasing wing of it. So it starts at negative 0.707 and it stops at 0. Oops, nice and clean. Because at 0, we have our absolute mins, so neither increasing nor decreasing at an absolute min. So just a little bit of the x-axis satisfies the requirement of the function is decreasing and showing concave up. So let's go on to the next problem. Part C talks about what would you see if this was current, and you can sort of say whatever you think you see. Fluctuations in current, ebb and flow, big negative patches, whatever you want to say that you see. It's rather subjective, and so as long as you have an answer that makes sense, you're good. Okay, on to Dell Computer. Quite a bit of wording to read, and I'm going to erase the board and we'll look at that problem. So problem number 2 on the practice test talks about the Dell Computer, and I apologize for scratching some things out on the copy because we're in the process of revising this to get some more recent data, and we're sort of straddling information. So I went back to all the old information about Dell way back in 1984, and I think it takes you up to about 2007. So given this big long function somebody found, and they called that the market share. So it says in 2002, in the old version, which we're going to use, we're just going to simply evaluate C of 2. In every place we see the T, we're going to put in a 2. I'm not going to write that because I know you know how to do it, and it is on the hard copy on Canvas. And so my answer, it came out to be about 27%. So the meaning of that is in 2002, Dell held or sold a large number of PCs, 27% of the market. And on the Canvas side, it says of all PCs in the US. So Dell was booming. And this is these personal computers. Okay, in part B, it says calculate the instantaneous rate of change, and as a calculus student, you know that means derivative, for 2012, scratched out to be 2002. So we're going to find the derivative and then plug in a 2. And again, apologize for any confusion back and forth between the revision. We're going to just stick with the old data. So for my derivative, I got, by using the power rule, negative 0.063 t squared minus 0.954 t plus 5.557. Plugging in the 2, we get 3.397, and that's again percentage because that's what the original formula was given to us to stand for. But this is change. So this is sales of Dell computers were positive, so it's increasing approximately 3.397%. So in 2002, sales of Dell computers increased because it's positive by, whoops, not dollars, percent. 3.397%. And if there's no harm in adding per year, even though we've said it's in that year, derivatives are always rates of change. So the rate of change is 3.397% per year, but specifically in this year. Alrighty, so I'm going to erase the board, or now let's move on. I'll skip camera for part C. So for part C, it says determine the absolute max and min for the time period, and we're going to go with 2000 to 2007. Write a sentence interpreting the results. So I'm going to go with my derivative, which we found to be negative 0.063 t squared minus 0.954 t plus 5.557. I'm going to force it to be 0 because the theory is horizontal tangent lines sit on maximum and minimum. So this is our tangent line slope finder, the derivative. Force it to be 0. This looks like quadratic formula. And I got t equals 4.49. I also got a negative, but I tossed that because negative years wouldn't make any sense. And I'm going to call this my critical value. And I keep emphasizing that because quite often students will stop and say, that's the answer, but it's not. It's where the max or min occurs. So I've evaluated my original function at the endpoints, which were 0 and 7, 2000 to 2007, and then also my critical value. And I looked at the output I got for the function. So this became 18.292, 31.726, and 26.615. So we look at all these and say who's the biggest, who's the smallest. So this is obviously the absolute max. And the meaning of that is, wow, Dell had 31.726% of the share in 2004 and a half, June of 2004. Where is Dell now? Do they still make Dells? So this is the smallest, so we're going to call this the absolute min. So smallest on this interval. Doesn't mean smallest ever, just smallest on the interval. Alright, ask us to make a graph of it. And the graph for this, actually, 2000, 2007, looks pretty much just like a parabola, and something like that. This was the min at the year 2000, and we could plot that down here. That's the min. It's all on canvas on the sheet you could print, so I don't have to bear with my bad sketches again. And this is when t is 4.49. That's our absolute max. And then the other end of the interval is at year 7, where we got 26.65. And I think I went a little bit further just for the purposes of the graph, make it smooth. So 26.615 there at 7. Max up here, 4.49, comma 31.726. And absolute min 0 at x equals 0 and 18.292% market share. There's another question about concavity in the second derivative, but you can tell that this, from the drawing, is a concave down function, and that at the top of a concave down function would be a maximum. Well, let's compute that second derivative. Let's go back to the other board. All right, so the last question about del involved the second derivative and a check for concavity. You said you could visualize that it was concave down, therefore that had to be a max right there. But if you do the math as well, you compute your second derivative and you plug in what you think is the max, if you get out a negative sign, which I did by evaluating it at 4.49, it tells us that we have a second derivative that is negative, therefore concave down. If it's concave down, we're looking at a max on top of the curve. Okay, I'm going to erase the board again. We will work on the problems with maximum fencing. This is the sketch provided to you on the sheet on Canvas for problem number 3. It's the one requiring the minimum amount of fencing to contain 7 wild animals that each require a pen of 30 square meters. And assume the pens are arranged linearly. Show the amount of fencing as a minimum by using the second derivative test. Okay, so we know that for the Canvas diagram, we call one distance y and one distance x, making a little square or a rectangle, because they're a rectangle, such that the area is equal to 30 meters squared. So to find area, we multiply the dimensions, length times the width, and we have to get 30. This is single variable calculus, so we want to be able to write one variable in terms of the other. So for example, on this one, I solved for y, and I said y is equal to 30 divided by x. That means every time I see a y, I can replace it with that. Because I want to write a formula for perimeter indicating all the fencing I would need, and I want to minimize that function, so I use the smallest amount of fencing possible. So to get the fencing, I know that I'm going to have these y's, 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to have x's 1, 2, 3, 4, 5, 6, 7, plus the other side, so 14x, and I call that my perimeter, or by that meaning the amount of fencing I need to go around the perimeter and enclose each animal. But I want to write a formula in one variable, so you can see on the sheet that I wrote a formula for perimeter in terms of x only. So that means when I get to this y right here, I'm going to replace it with this expression. Thus, I have a formula that says the same thing as this, the perimeter for the fencing needed. And let's see, we've tidied it up a little bit, got it ready for a derivative. So 240x to the minus 1 plus 14x And then the rule, the regimen is to take the first derivative, set it equal to 0. So first derivative, this is going to be minus 240 x to the minus 2 plus 14. And then we said we could rewrite this on this side, so positive 240, and the x to the minus 2 we can write in the denominator because it makes it look easier to find the solution for x by cross multiplying. So as a result of setting this equal to 0, we can rewrite this on the left side, leaving the 14 on the other side. So just looking at this part, ready to use the mechanics here. So that tells us that when we cross multiply, that 14x squared is equal to 240. And solving for x, we got x to be 4.14 roughly, whoops, 14, and inserting that back in for y, getting 7.25. Not the prettiest book problem, but perhaps a real life problem where you do indeed get decimals and fractions. And the final part of it I'm going to try to squeeze up here, not the best formatting, but they want to confirm that this is a minimum amount by plugging the x values into the second derivative. So what is our second derivative? It is going to be, looking at our first derivative, down here, minus 240 x to the minus 2 plus 14. Our second derivative is going to be negative 2 times negative 240 is going to be 480. And dropping this one more, x to the minus 3. Our 14 is going to be gone because it's a constant. And actually, you don't have to plug in any numbers because the numbers you're going to plug in here are going to be cubed in the denominator. And these are positive numbers because fencing is measured in positive numbers. And 480 divided by the cube of a positive number is going to be a positive number. And that means our second derivative is positive. And what happens to a second derivative that's positive? It's concave up. And what sits at the bottom of a concave up shell? But a minimum. So indeed we have found the minimum amount of fencing by making a width of 14.14 meters and a height of 7.25 meters. And if you want, you can multiply those together to ensure that you're getting 30 square meters for the pen. But it looks like roughly eyeballing it is going to work. Check it out accurately if you want. And found out that it's the minimum.